Okay, in the last video for the chapter here, 5.7, we're going to look at what are called enthalpies of formation. So there are many different types of processes you can have, different types of chemical reactions. So there's lots of different data for the enthalpy values associated with those chemical reactions and the different types. So you see here some of our examples. You have enthalpies of vaporization, which means how much heat, okay, you get out or you have to put in when you go from a liquid to a gas. You have enthalpies of fusion, which are melting, and you have enthalpies of combustion, and then you've got enthalpies of formation that we're going to look at here. So don't get too thrown off by the long names. Look at what is it an enthalpy of? Are you vaporizing? Are you fusing it together? Are you combusting it? That kind of stuff. Okay. Well, in this section, we're all about the enthalpy of formation, and what that is just what it sounds like. It's the enthalpy change for the reaction when something is formed from its constituent elements. So that means from all the elements that make it up, how much heat I would get out or how much heat I'd have to put in for that particular compound. Okay, so we're talking about going from an element or the elements to then the compound. So when we have these enthalpies of formation, we have to have some standards. Okay, I have to know what temperature, what pressure, what are the state of the reactants and the products in order to get then that compound that I want. So when we look at enthalpies of formation, okay, and again, like an example would be here, I'm going to take the enthalpy of formation, so delta H, and they usually put a little F there, for water. Okay, so I'm going to take and form water. So how do I form water? I take H2 and O2, and I will put together and make H2O. Okay, so it'll be the amount of heat that it takes to put those H and O together to make my water. Okay, so when we have these standards, we have standard states. And the standard here is 25 degrees Celsius and 1 atmosphere. So these enthalpy values were taken at 25 degrees Celsius and 1 atmosphere. Okay, if you see a delta H with a little like what they're called knots at the top, look like zeros or O's at the top, okay, that indicates that the enthalpy was measured at standard, which is that 25 degrees Celsius and the 1 atmosphere. Okay, so then if I see delta H not with an F, then that's the standard enthalpy of formation. All right, if its most stable form is present at room temperature, because 25 degrees Celsius is approximately room temperature, so I wouldn't have to put any heat in or get any heat out to make that particular element. Okay, that means then the delta HF for that is 0. So these are going to be things like H2, O2, carbon. Okay, their most stable form is a gas here, or is a solid. So I don't have to put any energy in or any heat in or get any heat out when I make those elements. So they're just 0. Okay, so let's look at this table and see if we can figure this out. When we look at this table, okay, we see all these delta H knots with the F. Okay, it's at 298 Kelvin and 1 atmosphere. When I select acetylene, I got C2H2, it takes 226.7 kilojoules per mole to put together and make acetylene. Now notice how it's per mole. Okay, standards are always when we're looking at 1 mole of a substance, which means a coefficient of 1. Okay, they didn't put in the ones that are 0 in here, but notice how I've got like HCl as a negative. I've got HI, which is a positive. So again, negative, you're getting energy out. Positives, I have to put energy in to do that. Okay, and then these are actually all in the back of your book. I believe they are in Appendix C, along with a couple other values like a delta S and a delta G. All we really care about is the delta H. These are not things you have to know. These are numbers that you will be given. Okay, and again, we're just looking at another way to calculate heat and enthalpy without having to actually do the reaction for these. So let's look at an example. It says, for which of the following reactions at 25 degrees Celsius will the enthalpy change represent a standard enthalpy of formation? Okay. For those or not, what changes would need to be made in order for the reaction conditions? So I'll look at this here. Okay, I've got Na, element, O2, an element. O is always a 2 when it's by itself. And I'm making Na2O. which is good. I have my elements, and I make the product, compound. Notice how I'm making 1 mole of the compound. So yes, this one was done at standard enthalpy. So I can get these values and figure out the standard enthalpy of formation. Now when I look at this one, look, I've got my element, and my compound. So good. But this has 2 moles. So no, that does not represent a standard enthalpy of formation. I would have to divide that by 2, and then you would. Okay? I've got my compound, it's a reactant, and I've got the elements as my products. So, no, that one doesn't work either. You'd have to flip it. Okay? Then I would have the standard enthalpy of formation for C6H12O6. So standards is just giving you a set of conditions, so that way I know all these numbers are following that same set of conditions. Okay, well now we're going to use these enthalpies of formation to calculate the enthalpies of a reaction, which is all I really care about. So I'm going to use Hess's law a little bit as well, and we're going to calculate delta H for a reaction. Okay, what you do is you start with your reactants, you pull them apart, decompose them, then you rearrange them to form your products. And the overall enthalpy change is the sum of the enthalpy changes for each step. So let's look at the example here, which is going to be the same one, C3H8, okay, which is propane. And hopefully this will maybe make a little more sense. Again, this is just another way to calculate heat, and calculate delta H. So you decompose your elements, okay? You take C3H8 and break it apart into carbon and hydrogen, okay? So my delta H for the first one is going to be this enthalpy of formation for C3H8. Next you form CO2 and H2O. Notice how I had to form 3 CO2s, so I've got 3 times the amount of enthalpy there for CO2. I had to form 4 water, so I got 4 times the amount of water. You look up the values for those particular compounds, and you add them up, and then you get your value. So let's look at the chart or the picture. So you start out with step 1 here. I got my reactants. I decompose the carbon. I decompose into the carbon and the hydrogen and the oxygen. I'm pulling them all apart. That takes that much heat I have to put in to do that. You're pulling something apart. Now I'm going to form one of my products, which gets me back so much heat. Then I'm going to form the next product, and I'm going to get back so much heat. And then you have an overall of this negative 2,220 kilojoules. In summary, okay, you're going to write these down. We have this formula. Delta H, not for a reaction, is the sum, it's a little e summation sign, it's the sum of N, which is just the coefficient of that particular product, whatever it is, times the enthalpy of formation for other products, minus the sum of the enthalpies of formation for the reactants. Products minus reactants. Okay? And you don't have to memorize this. This is actually on your green sheet. Some keys for this. Okay, this is the next part you want to write down there at the bottom of the page. Write your formation equation so that both elements are in their standard state, and you're going to have 1 mole of product. Break apart the reactants in their standard state and convert into the elements that are then used to form the products. So products minus reactants. Okay, we're going to do some examples, and I think you'll realize that it's actually not that hard. It sounds a little confusing right now. Okay, so if I'm going to calculate the standard enthalpy change with the combustion of 1 mole of benzene, which is C6H12, it says combustion, so I have to add O2 to form CO2 and H2O. CO2 is a gas, H2O is a liquid, C6H6 benzene is a liquid, O2 is a gas. So the first thing I got to do here is balance this equation. Okay, don't make it too hard. There are higher numbers here, but I always start with my carbon. Okay, I have 6 here, and I don't have 6 there. So I would start off and put a 6 here. Then I look at my H's. I've got 6 H's on the left, and I have 2 here. So there's 3, make 6. Now you hope your O's match. So I've got 12 O's here, and 3 more, I've got 15. I've got 15 O's. So there's no way I could take it times 2 with a whole number and get 15. So there's a couple of things you can do here. Go through and double everything and then it'll work out. Or you can take 15 halves times 2 is going to be 15, so then it'll work out. That's why I always say the O for last. If you don't like the halves, go through and multiply it, but what's going to happen is you have to have 1 mole of benzene here, so I need to go through and divide everything by 2. So this is my balanced equation. Okay, so the enthalpy of formation for my reaction, lots of subscripts and superscripts there, is going to be my products minus my reactants. So I take a look at my products. I formed 6 carbon dioxides. So I'm going to take 6 times enthalpy change, or enthalpy change for the formation of CO2, plus I also formed 3 waters, 3 times the delta H of formation of water, minus my reactants. Okay, and I have C6H6, so 1 times the C6H6 plus 15 halves times O2. Like I said, all these are in Appendix C if they are not in that chart in your notes. So all I do now is I look up my numbers. Okay, I look up and see what is the enthalpy of formation for CO2. Be careful, make sure it's the gas one. And you'll take 6 times, and you should find that's negative 393.5. Plus 3 times water. It's got to be water as a liquid. Okay, so that's going to be negative 285.8 minus, okay, my C6H6, which is 49, plus my 15 halves times my oxygen, and O2 is a gas at room temperature anyway, so does it take any heat there? So that's 0. So all I do now is put all my numbers together, and you should get negative 3,267 kilojoules, and it's labeled kilojoules per mole because it's per 1 mole of C6H6. Let's look at one more. You have 2 to do by yourself. Using the standard enthalpies of formation listed in table 15 or 5.3, calculate the enthalpy change for the combustion of 1 mole of ethanol. So again, products minus reactants. Look up the values and multiply by your coefficients. So delta H naught for the formation for a reaction is going to be my products minus my reactants, which is 2 times carbon dioxide as a gas, plus 3 times water as a liquid, minus C2H5OH, which is my ethanol, plus 3 times O2. So I'll look up my numbers. Okay, carbon dioxide, I'm going to take 2 times that, which is going to be negative 393.5, plus 3 times water. Water is negative 285.8. Subtract then my ethanol, which is negative 277.0, or 277.7, sorry. And O2, as always, is 0 because it doesn't take anything to put that one together. Add all my numbers up, and I should get negative 1,366.7 kilojoules per mole. Go ahead and try the last 2. You should get negative 1,207.1 kilojoules per mole. This one was a little bit backwards in the sense that you were solving for one of the things in the equation and you knew what the reaction was. Go ahead and try the last one. And for the last one, you should get CuO's formation to be negative 156.1 kilojoules per mole. And again, you're solving for one of the parts in this one. And it should then match whatever you see in the table. Notice how Cu and H2 are both 0 because that is their standard state at room temperature, is a solid and a gas.